neutron star black hole. That was about 200 megaparsecs away, and there were telescopes that were alerted to look for it. It was a little too far to be seen in electromagnetic radiation, but they looked for it. And also without Virgo, and Virgo is actually going to come on a little later because they had some technical issues. The localization is really poor, so it's hard to give a list of galaxies to look at. And we also had alerts the other way around. There was a supernova that happened relatively close by, about 6 megaparsecs, that LIGO is looking for. So right now it's in science mode and it's doing stuff. Okay, so the LIGO detectors in the US are, of course, it varies by day. Sometimes some things happen, and so there's some problem with the power or with something in one of the detectors. But it is. The science mode is going on. My work as a researcher has been, what will LIGO see next? So in 01, 02, 03, they have seen black holes, neutron star black holes. And so the question is, what are the other things that will be found? Trying to predict them, to model them. So one thing that we see with electromagnetic radiation, right, is lensing. When you look for planets, when you look for galaxies, you see lensing. So the farther gravitational wave detectors will look, the more likely it is that a good fraction of your events will be lensed. So there will be stuff between the source that emits gravitational detector, between that emits gravitational waves and Earth. And that lensing might modify the waveform in a visible way, or it might be a more subtle effect. For example, you could think that the black hole is 50 solar masses, but in reality, if it's a redshift of 2, then you divide by a factor of 3. It's 1 plus z. In the detector frame, you see 1 plus z times the mass in the source frame. Okay, so if it's farther away, even if the waveform isn't modified, it might appear more massive. I'm not working on this alone, obviously. The other people at the University of Barcelona working on lenses, on gravitational lensing, in particular, Helena Uba, who is a PhD student. She's very talented, and she has done work with me and with Oleg Bulashenko, who is a professor at the University of Barcelona, and Andrew Lundgren from the University of Portsmouth. He is the LIGO expert who is helping us along and competing with us because we are Virgo. No, not quite. Okay. In fact, we have students who are doing LIGO shifts right now because Virgo is off. Helena and Dani, another student, is on call this week looking for events from LIGO. So they're actually looking at the data and seeing if there is a gravitational wave or if there is some forklift or some truck going by, checking the quality of the data. Okay. And so what has LIGO seen? This is a picture of the stellar graveyard. So look, gravitational waves is kind of like doing archaeology. You look at dead stars. So it's like looking at a skeleton versus the whole person. Okay. And the first thing that surprised us was that the black holes that LIGO has seen were more massive than anything that we have ever detected in X-rays. So if you look at the bottom of this plot, you will see the X-ray electromagnetic neutron stars and black holes. And with LIGO, the blue part. Okay. And so in our galaxies, we've seen black holes. In our galaxies, we see black holes of the order of 10 solar masses, a little bit smaller, but of that order. And with LIGO, the average black hole that we see is 30 solar masses. And as we accumulate more events, now we expect we'll see more massive black holes, even more massive black holes. So these black holes were never observed with anything else before. And even the neutron stars that we have seen, one of them was the standard 1.4 neutron star, and the other had the different mass ratio. And so there is some difference. Okay. And the question is the difference physical, or are some of these events lensed? Okay. Or my guess is that it's both. So we look at our galaxy, right? So our galaxy, for example, has relatively high metallicity. High metallicity means that black holes could be smaller. So if you have an older galaxy with lower metallicity, you could have black holes, stars that grow bigger and collapse later. And so black holes could be bigger in older galaxies. So it's just like looking for planets. If you look for planets and you look, for planets that are exactly at the Earth, you will miss planets around other kinds of stars and so on. And so, but on the other hand, you have to know what you're looking for when the data is messy. So it's a balance. Okay, so this is usually with LIGO, we look at this frequency versus time, the power in the frequency versus time plots for the events that we have seen. So you can see in the beginning, in the first run, there were few events. In the second run, there were a few more. And then the most of the events were in 03, which was the third science run, which was actually stopped, not because there was a problem with the detector, but because of the pandemic. So they had to close LIGO and just like everything else, just like they closed grocery stores and all of that stuff. They closed LIGO as well. And in 04, we're expecting to have a lot more gravitational waves than we've had so far. Okay, but if you look at these pictures, they do look a bit smeared up, right? So the question is, are they lensed? Okay, so this is, you can't say that they are, but you can't say that they aren't. So when I looked at it, I thought, okay, it's a good thing to think about. Okay. Okay, so one of the arguments that was made, especially in Spain, Joan Garcia Bellidos is a big promoter of black holes of primordial origin. So he's saying that because these black holes are different than what we have seen before, they could be of primordial origin, coming from very early universe, and we would see their first merger. Or it could be that they have grown in a different environment from the Milky Way. And we know that there are different galaxies out there. We know that some have lower metallicities than Milky Way. And stellar collapse is a complicated business. There are a lot of parameters. Okay, or it could be that they're lensed. My opinion is that it's a combination of at least the last two hypotheses. About the primordial black holes there, I don't know. Okay, it may be or it may not be. It's difficult to know. Okay, but there are ways to guess at it. Even at that, if you find black holes that are eccentric, they are more likely to have lived in clusters, and then they're more likely to be perhaps primordial. So, as LIGO finds more sources, we'll be able to disentangle some of these scenarios and perhaps find what fraction of black holes come from where. That's my guess, that it will happen, that it won't be just one person is right. Okay. Okay, so it is clear that there will be lensing because there will be stuff between us and the black hole we're observing. The question that I have is not if there will be lensing, but when is this lensing detectable? When will we be able to tell that the waveform is lensed? Okay, and also how much lensing will there be? So, if I look at the distance, how do I believe it? Okay. Because for black holes, there is no electromagnetic counterpart. So if you see a neutron star binary, you can find it you may be able to find it in other ways if it's close enough. But if it's a black hole, then it's far and it's dark. Okay, so you only have the LIGO data. Okay, so what I looked at was at the simplest lensing model that there is, which is the point mass lens. Okay, so what happens there is that you have a transmission factor that alters your waveform. And the lensed waveform is the transmission factor times the unlensed waveform. Okay, and the transmission factor is relatively simple, it's analytical. And then you can compute the SNR increase, so how much the SNR can increase because of lensing, and you can compute the mismatch. So how different will the lensed waveform be from the existent waveforms in the template bank? And then we've also looked at the effect on the strain, just the pictures to see how lensed waveform looks in this microlensing case. So microlensing case means that the object between you and the black hole or neutron star binary is a microlens, so it's a compact object. Okay, and then what is the probability that we'll see it? What is the distribution of lens sources out there? Okay, so here we computed the signal to noise. So the top plot also shows the signal to noise as a function of lens parameters. So the mass of the lens is at the bottom, and on the other axis is how close you are to the line of sight. So these are the two parameters that determine entirely determine your lensing. So
can we move the video since it's on top of the
yeah, on top of the plot. Let's see if it allows me to move. Okay.
or minimize it?
Yeah, maybe I should do that. The first one?
Yes.
Okay, better. Then I have to put it here, and then it won't be disturbing. Okay, so and depending on the value of these parameters on the mass of the lens and of how close, how far you are from the line of sight, you can be in different regions. So there is a region when there is only amplification. So if the transmission factor grows in this part, then it only amplifies the waveform, but it amplifies it in a frequency-dependent manner. This is the transmission factor as a function of frequency. Okay. And then you have a transition region, and afterwards you have a region when you can average out the oscillations and assume that the transmission factor, it's a very good approximation. The transmission factor is basically the average of this. So you have some minima and maxima, but on average, it's a simple function, basically something like 1 over y. Okay, so in the geometrical optics region, it only depends on the closeness to the line of sight, and in the amplification region, it only depends on the mass, on the mass of the lens. So in the geometrical optics region, it's independent of the mass of the lens, and in the amplification region, it's independent of how far you are from the line of sight. And then there is a transition region where it depends on both parameters more. So and you can see that it's a fairly resilient calculation, so it doesn't depend because it's basically a ratio, so it won't depend on the noise curve used very much or on the mass of the black holes, of the black holes in the binary. And of course, so this is the SNR increase. So it means your signal to noise increases by a factor of 2 if you're on this line, okay, a factor of 4, a factor of 10. So of course, the higher the mass of the lens here, the higher the SNR increase as expected. Okay, so ideally you want to have sources that are close to you on the line of sight, and then they're massive, as as expected. But it's a fairly simple parametrization. Okay. Okay, so this was okay, and we've seen that the SNR increase if you go to from four lenses between a few solar masses and 10 to the 4 is up to a factor of 10. Okay. Okay, but then what is the mismatch? So how different are these lensed waveforms from unlensed waveforms? Okay, so you can compute the mismatch, and you can see that it can be significant. So it can be of the order of 80%, 70%, or 90%, depending on which region of the parameter space you are. And so, for example, here we vary the mass of the lens. So at a certain point, you can see, so I started at 30, and if at a certain point, when you get to thousands of solar masses, it stops mattering because you're switching to the geometrical optics region. So increasing the mass, if you could increase the mass of the lens, then the SNR increase doesn't change anymore. So so here for a mass of the lens of a few thousand, you get an SNR increase of factor of 2, for example, and beyond that it doesn't change anymore. And this is a fairly significant mismatch of 80%. Okay. So what we've shown is that it's not impossible to see lens sources, that there is a mismatch and that that mismatch could be detectable. Okay. Because there are also areas where the mismatch is very small, and so you'll see that. But first, let's look at how does a lens gravitational wave look. So at the top, you have the unlensed gravitational wave. So you have the in spiral, then the merger, and the ring down. And this is a standard 30-30 solar mass black hole. Okay. And so if the mass of the lens is relatively small, you see a minor amplification of the signal that's frequency dependent. That's very difficult to distinguish. So you won't see it. Okay. So as the mass of the lens gets bigger, the amplification becomes more significant. It's a function of frequency, so it amplifies different regions of the waveform differently. Okay. And once you get to of the order of a thousand or a few thousand solar masses, then you get the beating pattern. So here you're already in the geometrical optics approximation. And you can predict where the maximum and minima are analytically for this point mass model. So it's a relatively simple model, so you can predict the dark spots and the white and the in principle. Okay, and then as you increase the mass even further, the two images will separate. You'll have two separate images. And then eventually you get into the strong lensing regime. What is likely to happen is to have strong lensing, perhaps mixed with microlensing. So perhaps not one or the other. Okay, so this is an injected lensed waveform at an SNR of 10. So I'm just showing it to say that it's not always as clear as or as pretty as in the previous picture. This picture basically assumes an SNR of 20 or more. So when you see it clearly. Okay, and here it's more what the first events we'll see will be very close to threshold, and now the detectability threshold is about 8. So you won't be able to identify lensing by eye. It just helped us in understanding the problem. Okay, so what is the probability that an event is lensed, and what is the distribution of lensing? So we can do an integral, and we can integrate up to so we can integrate over all events that are at a fixed threshold or above this threshold to see. So what are all the lensed events above SNR of 10? Okay. So you get a distribution of events. And so this is the function of redshift. So the question is, what kind of redshifts would you have for lensed gravitational waves? Okay. And from our simulation, assuming the point mass source, you get redshifts of the order of 1, 1.5. So the first plot shows all lens sources, whether they're detectable or not. Okay, so the first row here shows all lens sources where I'm varying the mass of the black hole. So here we will have a binary that's perhaps 15 solar masses, then 30, 60. The binary of the black holes that are colliding. Okay, so this is all the lens sources. Okay, so you can get redshifts up to 2.5 maybe for the more massive case, or 3. And then if you want to have a mismatch of at least 5% so that you can potentially see it, then you see that your space of lensing of lensed objects becomes much smaller. So most of them are silent. There are some that are detectable, and the ones that are detectable are generally at lower redshifts than the ones that aren't. Okay, and here you see the two regions. So one of them is the geometrical optics, the other one is the amplification only, and the one that's weaker is the amplification only region, where you're just amplifying the signal without creating the beating pattern. Okay, and if you want to have it really detectable, which is like 10%, so my guess is that when we first see lensing, it would be a significant mismatch of 10%, or because the first time it's identified, then your space goes down. This is 1550 solar masses, and here 3030. Okay, and the more massive, and in the more massive case, you also have the problems that as the black holes get more massive, the waveforms become shorter. So it's harder to see at a certain point. More mass doesn't gain you more. The waveform becomes very short, and it's harder to see deviations from it. Okay. This is the function of y, and so y is the proximity to the line of sight, so how far you are from the line of sight, and the mass of the lens. Okay, so it means you're expecting to find events that are for lens masses of the order of at least a few hundred, and for y's of 0.1, 0.5. So in general, less than the candidates we have seen for O3 for the lensing papers that LIGO has already published. But the candidates aren't strong candidates for lensing. So okay, so and last is the question is how many events are lensed, right? So if we integrate over all the lensed events, here I made a bold assumption of assuming that all that matter is in point mass lenses. Okay, so it's an upper limit. You can have 20% of your events could be lensed. And out of those 20%, you would see 4% of them. Okay. 12% of them will show a mismatch of 10% or more. So that means right now we've seen about 100 sources. That means that at most 4 would be detectably lensed. Okay. If all dark matter was in the whole system. And the fact that they haven't seen any lensing is consistent with this expectation. However, if you have 1,000 sources or a few hundred sources, then you will detect lensing. So I believe they will find gravitational wave lensed events soon, whether 04 or 05, but and there are searches for lensing. They're searching for lensing. Okay, so the question is how to build the optimal search. This is why I looked at the parameter space. Okay, and at the moment the search we have favors events at high Y, because the events are distributed uniformly, and distribution is something like Y dy, so that favors events that are not close to the line of sight, whereas lensing favors events that are close to a line of sight. And so we need to build a search that is more sensitive to events that are closer to a line of sight, basically. And also be able to identify more complicated things like embedded lensing, where you have more objects, strong lensing mixed with microlensing. We can imagine that the universe, especially the electromagnetic universe, isn't as simple. It won't just be one black hole between us. And if you look, 5 gigaparsecs away, there may be more things in between us and the source. And so there is room for more modeling, and we hope to find gravitational lensing soon. I think that's it.
So we can go to questions.
Can you go to the mismatch definition? Yes, so what I understand is that the mismatch that you compute is with respect to the true source, with respect to the whole template bank.
It's the mismatch with respect to the whole template bank. So you look, you try to find the closest match in the template bank to your lensed waveform. So you loop over all your template bank and find the one that the maximum match. And the mismatch is one minus the match.
And which template bank have you used for this?
So just the standard, what they're using right now to detect gravitational waves. So the standard. It's a combination, right? It's called IMR phenom or INM phenom XIS, depending on what your favorite model is. But it's similar. So yeah.
You take it from this.
Yeah, I'm using the LIGO software, the PyCBC LIGO software, because I mean we want to be as close to a search as possible. We don't want to make up our own waveforms. But we do have a numerical activity group at UB, Thomas, Andrade, and so they do simulations of eccentric waveforms, and I work on that as well. So they again we compute the mismatch and we look at that, but it's a different project.
No, I asking you. I'm not sure where this was higher harmonics, something like this, which we know that typically they break the general system in like this.
Yeah, I focused on one effect at a time. When I do eccentricity, I do eccentricity. But yeah, I mean, ideally you can do a lensed eccentric waveform or higher harmonics and lensing or precession and lensing.
From parallel.
Yeah. So, but this was the first paper I wrote on the topic, so I tried to say, what is the parameter space? And nobody has done this before. Like nobody looked at all the parameter space and made a plot like this. What is the SNR increase as a function of lens mass? Like it was a question that I wanted to answer. Like, when I first looked at this, so how much farther can you see because you're lensed? And so nobody else had done it, so I made this plot. Okay, but it is not, people have done more complicated models and have done a lot of work. It's just that they haven't tried to get a big picture.
No, I wanted to understand. The other thing is that all these estimations are only dependent on the model of the wave.
Well, that's the thing. It's relatively model independent in the sense that you see it cancels out because it's a ratio. And so depending on, as long as you are within the LIGO range, like if you're going to do Einstein telescope, this curve will be different because you have more low frequencies, right? In ET. And in fact, we can do that because we are in ET. Yeah, it's a different noise curve, but within LIGO, whether it's O2 or O3 or O4, I mean, I can't tell the difference between the red and the black very well. Okay, maybe. To me, they're like, okay, it's the same. And when we varied the mass, it was the same. So there wasn't much variation. So it was fairly robust because it's a ratio of the lensed and unlensed. This is the SNR increase.
Yeah, thank you very much for the talk. So you mentioned that we haven't seen lensed gravitational waves.
No, we haven't.
We know that, but I got the impression that we don't have the lensed templates. We already searched for those.
There is a lens search, and there was a lens search in search in O3 and O3B. So both papers are published, and there are some candidates, but they are candidates at y equals 1. They're not consistent. I mean, and they're not very different. So there's basically they are candidates, but we don't think they're actually lens. But maybe they are. I don't know.
Okay, and you mentioned that there is a difference in the measured mass. So,
right.
So there is also a difference in the effective spin.
So what you observe, right? When you observe in the detector frame, right? Not in. So you don't know what is in the source frame.
Yeah. Sorry, I will rephrase it. So if you have a lesson bank,
right?
And you don't know that it's lensed, because you mentioned that it might be higher amplitude or not.
Yeah, you can't tell. I mean, yeah, most lensing will be silent. So, most cases you won't know that it's lensed. But in some, very few cases you will. So we hope to see those few cases. Yes.
Yeah, so what I'm gonna say here is that people, when are looking to get the different contribution from different scenarios,
Right.
for example, the primordial black holes,
Right.
it says, okay, you have to assume unknown physics there. Okay, so
Right. Which we don't know.
there is also
Yes.
the dynamical formation.
Yeah,
which
sure,
is
sure.
very important.
Yes.
So when they look to see what is the origin of the black holes, they look at distributions of the
Spin exchange.
mass and the effective
Yes.
spin to see the.
Yes.
So I guess that if you know what is the effect of the lenses, you can see the contribution of the less events into the total distributions, right?
Yeah, I mean, that's what I tried to do at the end. Right, so these are the lens threads. Okay, so about 20% of events are lensed if you assume all dark matter is microlenses. But yeah,
Thanks.
Generacy of the mass is very different.
Yes, but this is interesting because you have the relative distribution log with a mass and the effective speed.
Yeah,
You can,
but for this, you will need much more precision than for this
listen.
and right now I mean, LIGO can find spin, but there are very few. It's mostly consistent with zero spin, so there are not very many spinning black holes. The same way with lensing, there are some candidates, but
So the sensitivity right now, you said was around 8, not nice.
well, no, I mean the detect. So when do you assume a detection? So if the SNR is greater than 8, you assume it's detected. But the sensitivity is the sensitivity to, they code it in megaparsecs. It's usually the sensitivity to neutron star binary. That's what usually coded. So I mean, between O3 and O4, it's a little less than a factor of 2. Right now, it's doing a bit better than O3, but not a whole lot better. So, we've seen the neutron star black hole at 270 megaparsecs. And this was, at an SNR of 9 or 10 or something.
Any other question? Okay, so let's thank the speaker again.